Hello, my name is Neil Kolker, and this is my final report for optimizing a composite I-beam design. The objective of my project is to develop a tool that can be used to create a preliminary design of a composite I-beam. The tool will be useful for developing an initial design in the iterative design process. I'm going to design a constant cross-section cantilever I-beam while minimizing the deflection at the end of the beam. The beam will be made of carbon fiber and will have a symmetric cross-section. The variables affecting my model will include the area moment of inertia, which will be based on geometric properties, the elastic modulus, which is calculated based on the layup of the laminate, the load applied, the number of plies used for the buildup of the flange in the web, and the length of the beam. I've made assumptions to simplify the project. The I-beam design will consist of 3 laminates bonded together to get the I-beam cross-section. So it'll have 2 flanges of equal width and a web. The laminates will be balanced and symmetric and will be quasi-isotropic, which means the same material properties will be in the in-plane direction. The elastic modulus of the composite material will be determined based on the ply layup. A smeared modulus is calculated using the moduli of each laminate to get a modulus for the full buildup of the cross-section. This tool was built using MATLAB. Laminate properties based on buildup of the flanges and web were calculated. Using composite laminate theory, elastic and shear moduli of a symmetric and balanced laminate are calculated. For simplification, discrete values of moduli were calculated based on the thickness of the laminate. Using the calculated moduli of the flange and web, a smeared modulus, or average, for the whole cross-section is estimated and used to get deflection. The beam is treated as a homogeneous composite structure with an estimated modulus. The modeled problem is then solved using genetic algorithm. To demonstrate the functionality of the tool, a cantilever I-beam made of carbon fiber was solved under a simple point load at the end of the beam. Given variables were length of 5 meters and an applied load of 3,000 newtons. For the constraints, the laminate buildups will be in sets of 8 plies of ply thickness 0.25 millimeters. The ply layout will be 0, -45, 45, and 90, and symmetric. The moment of inertia I must be less than 200 times 10 to the 6 millimeters to the fourth. Moduli from a table of discrete values was selected and used. The geometric constraints for this problem are given in the table. The genetic algorithm completed after about 375 iterations. For the given problem, the optimized cross-section is as follows. Flange thickness of 48 millimeters, flange width of 495 millimeters, web thickness of 50 millimeters, and web height of 78 millimeters. The resulting deflection of the beam was found to be 2.73 millimeters. The plot on the right shows the convergence of the genetic algorithm. While the tool shows basic capability, the tool can be expanded for multiple materials, varied ply orientations, and even additional loading conditions. Potentially, other methods of developing a modulus estimate for the structure can be considered as well that could perhaps give a more accurate measurement of the moduli. Thank you.